We're now ready to do our first meaningful computation. We have now all the infrastructure. We know what gates are, we know what circuits are, we know how to go from a truth table, input, output, sub-expressions, expressions, draw a circuit. Okay, so now let's actually build first small but at least meaningful computation. So we're going to build what's called a one-bit compare for equality, a CE circuit. So what do I mean first of all by one bit? I mean I have my inputs are A and B, which are each a single bit. It's either 0 or 1. A 4-bit compare for equality, which we'll do in a little bit, would be that I have A is 0, 1, 1, 0, and B, for example, is 1, 1, 0, 0. And all I want to do is ask, are these two one-bit values, A and B, equal or not? And so here's my little pseudo code for the computation. If A and B are equal, then return 1, otherwise return 0. Notice everything's binary. A and B can either be 0 or 1 because everything's in binary representation, and my output is either a 1 or a 0 depending on if those two bits are equal or not. So pretty straightforward. So now let's start turning the crank. Let's figure out how to design a circuit that does this. So step 1 is what? Build a truth table. What are the first two columns of the truth table? They are my inputs. I have two 1-bit inputs, A and B, and I have a single output C, which is going to be equal to 1 when the two bits are equal and 0 otherwise. Okay, so the first part of this is easy. Simply enumerate all possible set of inputs. 0, 0, 0, 1, 1, 0, 1, 1. And you should do it in this order, by the way, because it makes sure that you don't miss anything, and it's just good discipline, and it's the way everybody else does it. So the inputs are trivial. Just count in binary from 0 to 2 to the n minus 1. Now you got to tell me what the output is. So this is the work. Tell me what you want to compute. Well, what do I want to compute? Let's go back to the previous slide. I said I want this to be a 1 when these two bits are equal and 0 otherwise. All right, so here they're equal, not equal, not equal, not equal. So now I know what my output is. It's a 1 in the first row, 0, 0. It's a 1 in the last row, 1, 1, and it's a 0 otherwise. So this is now a meaningful computation. It's simple, but meaningful. It's telling me if these two bits are equal or not. Okay, good. We've done step 1 of our 4-step circuit design. Let's do step 2. What does step 2 say to do is to build for each output column, there's only one output now, a sub-expression. Okay, so let me remind you how we do that. We isolate where there's ones. We go figure out what is the combination of and not that gives rise to that one, and then we move on to step 3 and then step 4. So let's just do the sub-expressions for now. All right, so there's a 1 here and a 1 here. So this is the only place I have a sub-expression. So what do? I go back to the input. That's a 0, so I not A. There it is right there. That's a 0, so I not B. I AND those two together, and again, remember that why this works. Because when A is 0, not A is 1. When B is 0, not B is 1. So when I AND 1 and 1, I get 1. And that is the only place I get 1. There is no other possible values of A and B that will give rise to 1. So this is this very surgical strike, this little sub-expression. It's going to evaluate 1 here and only here. This is somebody else's problem down here, and this is nobody's problem because the default is going to be that everything evaluates to 0 if it's not this or not this. All right, let's build that sub-expression. Again, go back to A and B. That's a 1, so we bring the A over. That's a 1, we bring the B over. And again, this sub-expression is 1 if and only if A is 1 and B is 1, and it is 0 everywhere else. So again, notice why we like the ands here, because for any value that is not 0, 0, and any value that is not 1, 1, these expressions are going to value to 0. So here, for all other values of A and B, this evaluates to 0. Here, all other values of A and B evaluate to 0. So I get these two for free by simply these being so surgical and evaluating to 1 if and only if we're here or we're here. Good. So step 2 is done. I now have the sub-expressions. So let's do step 3. Combine the sub-expressions with ORs. For each output column, of course, we only have one output column. So C, my output, is going to be equal to not A and not B, there it is right there, or A and B. And again, you have to convince yourself that this is exactly what you want. Okay, so again, this can be 1 in only one situation, this row right here. This can be 1 in only one situation, this row right here. So this entire expression will be 1 in this case, and again, notice it's 0 everywhere else. We sort of came for free because of the nature of the AND. So there it is. I've got a little Boolean expression that is what? 1-bit compare for equality. So at this point, you're sort of done. Drawing the circuit is just the fun part. It's just to sort of prove the point that you can actually implement this thing. But I've now got a computation, 1-bit compare for equality, using logical AND, logical OR, and NOT. All right, let's go ahead and just draw the circuit. Okay, again, input on the left, output on the right. There's 2 in. This is a 1-bit compare for equality. I'm only comparing 2 binary numbers. And here's my output, and I've brought over my expression here just so we can carry it over. Okay, so we know there's going to be an OR somewhere over here. There's going to be 2 ANDs here, and I need a couple of NOT gates for the A and the B. Okay, so let's go ahead and just start pulling these pieces together. All right, so let's see. I'm going to take A and B, and I'm going to shove them into this AND gate. That's this sub-expression right here. Okay, that's the easy part. I don't need any NOTs. And now I'm going to peel off A and B. Again, filled circle when I peel the signal off, open circle when I cross the wires. You have to do this so you can follow the inputs. So when you follow this line, you know to keep going here. You can ignore that. And then it goes into a NOT gate and it goes into an AND gate. Same thing with B. I'm going to peel it over, drive it into a NOT gate, shove that into an AND gate. Don't forget the dot on the AND gate so we can see what you're doing. And this, of course, is not A and not B. This is A and B. I, again, like drawing these the actual expressions here because it sort of reminds me that, you know, what I'm doing, and I can go back and check my work nicely. Now, these two, of course, so this sub-expression corresponds to this. This sub-expression corresponds to this. And what do I want to do with those two? I want to shove them into an OR gate, and then I have my output. All right, good. Shove them into an OR gate. That's now the full expression, and I have my output. And now we have our first meaningful computation. It's incredibly simple. It is simply a 1-bit compare for equality, but it's meaningful. It actually does something. Okay. And notice here, in some ways, there's something I always think magical about these designing these circuits, because notice that you're not really computing 1-bit compare for equality. What do I mean by that? What I mean by that is you've sort of memorized 1-bit compare for equality. That truth table in step 1 gave the computer the answer. What did you say? You said, look, here are all possible sets of inputs, 0, 0, 0, 1, 1, 0, 1, 1. And here's all the outputs associated with that. So when you see 0, 0, output 1. When you see 1, 1, output 1. And then all the other times output 0, you gave it the answer. And now what it's doing is simply, I mean, it is computing it because it's pushing it through the circuitry, but you're the one who did all the hard work. You're the one who told it what the answer is, and now it's simply doing that for all possible inputs using these operations. So in some ways, this is sort of the magic of circuitry, is you're actually doing a lot of the hard work in the designing of that truth table, building the sub-expressions, building the expressions. Eventually, we'll see how to simplify those things to make them more efficient. And then this is just sort of turning the crank. It's just simply implementing the machinery that you actually designed. You gave it the answer. Okay? All right, good. So this is the first and simplest now where we've actually done a meaningful computation using our 4 steps. Input, output, build the truth table, sub-expressions, combine the expressions, draw the circuitry. And what we're going to do now for a little while is we're going to just do a lot of examples. We're going to see how you get more and more complex computations. And then near the end, I'm going to show you, because I'm sure some of you are already thinking about this, is, you know, there's going to be at some point there's going to be a lot of these gates. And how can I make them simpler? Is this really the best way to design circuits? And the answer is absolutely not. This is not the best way to design circuits. Circuit design is incredibly complex, and you really want to optimize it so that you get the most amount of bang for your buck on a circuit. We're going through the simplest possible circuit design. I'll show you a couple of optimization techniques near the end of the class here. But until then, we're going to do a bunch of examples to make sure we understand this 4-step process. All right, that's it for now, and we'll pick it up in a few minutes. See you soon.